record this on this computer. I should be able to do that just fine. All right. So notice it says, I'll take more specificity for gathering data. It's always been like, so here's what I want you to do for this one. It's, the premise is I want you to implement insertion sort, quick sort, and one other sorting algorithm from the list below, okay? So what does that mean? What does that mean? It means that essentially I want you to go ahead and go online and find implementations of the language you choose of insertion sort and quick sort and any one of these other sorting algorithms, which are very well known: shell sort, merge sort, heap sort, and team sort, okay? Where would you find source code for these things? One great place is Rosetta code, okay? But you can't just like straight up take it. I mean, first off, you want to cite where you got it from, just because that's academically proper, even if your professor is giving you permission, right? But like, say I want to do insertion sort. Rosetta code is a place where basically you can see where common algorithms are implemented. So insertion sort it has the pseudocode, right? And look at all these languages. These are all languages that think that this has been done in. So let's go ahead and take a look at C, and we see that this is a insertion sort for an integer array C, right? And this is it's one possible implementation. Here it is in C#, in C++, right? And then we can also see in Java as well, right? Here's an insertion sort for Java, okay? It's not stable due to the lack of an upper bound binary search function. So, oh yeah, using some built-in algorithms, which you don't want to do. We want to keep it stable. Insertion sort is one of my favorite algorithms because it's stable and it's online. So what does that mean? Stable means that basically if I were to give you a deck of cards, right, and I wanted to sort it, right, if in the unsorted deck, the King of Hearts was followed by the King of Spades, then when it's sorted, the King of Hearts will be followed by the King of Spades. But if I've sorted, but if I give you the deck and the King of Spades comes before the King of Hearts, then the King of Hearts, then the King of Spades is going to come before the King of Hearts. So two things that have the same value will be in this, they'll end up in the same order in the input and in the output. It's very obscure as to why you might need that, but it helps to know whether the sorting algorithm will guarantee that or not. This doesn't really matter for like purely numerical data. Like if I'm sorting a list of numbers, there's no way to tell the difference between the first 5 and the second 5, so it doesn't really matter. It's also an online algorithm. So even though it's really it's n squared, which isn't that great compared to other sorting algorithms, right? It has this nice feature where basically if you have a bunch of data and then you have to sort that data with a bunch of more data that you already have, you don't have to sort it start over the process completely. Or if you have to add one more item to the entire thing, you can use insertion sort. It's only one additional more run. You don't have to restart the sorting process if you get more data on it. So in other words, like it could just continuously receive data and sort it, which is pretty cool. It's not a feature other sorting algorithms really have. Also, even though it's n squared, it's really efficient if in realistic data sets, because in realistic data sets like temperature, in temperature, it's not going to be completely random data sets, right? With temperature, you're dealing with something that looks like this, right? The temperatures go up and down, up and down. It's a continuous function. But with random data sets, they'll have like stuff like this all over the place, right? So in a realistic data set, this insertion sort's great because it's able to really take advantage of these runs just by the way it works. It's pretty cool like that. Also, when it's a small algorithm, small thing, it runs very efficiently. This may or may not be relevant to the final exam because I'm a big nerd when it comes to insertion sort. There's a reason we teach the algorithms that are O of n squared even though the best sorting time we can get is n log n, probably, with some caveats there. If we have if we are not parallelizing the sorting process, then really the best runtime we can really hope for is n log n. If we parallelize it, though, there's a bunch of research in that area, and a bunch of solved problems in that area. For instance, we know, like, given 16 items and n processors, how n processors running in parallel, what is the most efficient way to sort things? It's one of those kind of really cool things that we figured out. All right, but anyway, what you're going to want to do is you just simply take this algorithm, say copy, and plug it into your IntelliJ, and you're like, aha, and I'm done. Except, of course, you want to cite it. Just simply say where you got it from. But that's just the first part, right? Then I need you to modify the sorting algorithm to keep track of the number of comparisons performed, the number of exchanges performed, and the total runtime of the algorithm. So let's kind of take a look at what that might be. Now, okay. So what is a comparison and exchange while this is loading up, right? Well, if you haven't had the chance to watch the videos, a comparison and an exchange are the two ways we can measure in big O time the runtime of an algorithm. Okay, so a comparison is asking, are these two items in order, right? Are these two items in order or not? Is one value less than another value? And an exchange is, we have two items, we need to swap their position. Now, these are the two things we care, the two costs of sorting, okay? So let's go ahead and do this. And no worries, Maxim, I've been recording, so if you've not been able to fully listen on your phone, okay? So this is how I would, if I was a student, how I would kind of go about doing this assignment. So this window, so, okay, comparisons versus exchanges, right? Now, why do we care about, so in general, what we care about is comparisons and we don't care about exchanges. Why? Because in general, comparing two items to see whether they are less than or greater than each other, that could potentially be more expensive, right? Because if you're comparing two very complicated data types, that might require a lot of checks to do to see if one comes before another, right? Versus exchanges are easy. You just swap two values in memory. That's no problem for a computer. But say you're working in the physical world instead, and like you're sorting large boulders, right? In which case, you really want to care about that number of exchanges, and you care less about the number of comparisons, right? And that might be where something selection sort wins up. So let's go ahead, and I will kind of, so let's go ahead and grab our sorting algorithm here, the insertion sort, copy, okay. Okay, and I'm just going to show you this because I want to give an example of what I want as kind of the data that I want to collect. Sorting, okay? So, because this is actually more about data collection and learning how to do data collection. So, public class sorting, what we're going to do here is, here's insertion sort. Copy pasted it in. Okay, let me go ahead and cite it. Okay. Code from, or I'll be even more specific, this method from, and boom, cite it. Okay, and again, I'm explicitly telling you to go ahead and do this for the sorting out. That's perfectly fine. It helps to go through and write them yourselves, though, just so you get a good understanding of them. Okay. So what we want to do is basically keep track of the number of comparisons and the number of exchanges that this method, that when we run this algorithm, it will do. So what I'm going to do for that is the way I would do it. Well, there's two ways you can do it. You can have a static int num comparisons, right? Make sense? The static int num comparisons, right? And static int num exchanges, which is probably the easiest way to do it for quicksort. The way I like to do it though is to have a private class, because it allows me to kind of avoid. It keeps things straight. Private class, private static class data. Okay, and it's just going to have two fields: int comparisons, int exchanges. This is less a class and more a struct, like from C, if you're familiar with that. So that's it. That's all I need to do because it will initialize to 0. And what I'm going to do is that I'm going to go ahead and for my sorting algorithm, what I'm going to do, this is actually the even better way to do it, so you don't have to modify the return values or anything. For my data collection purposes, I'm going to just simply pass in a data object to keep track of everything. So data, okay? Okay, so I've got this. Now it says I want to modify the algorithm to keep track of the number of comparisons, number of exchanges, and the runtime. I'll tackle the runtime in just a second because that's super easy. Okay, so what we want to do is whenever we compare two values to see whether they should be swapped, which is what's going on in this algorithm over here. So whenever we're going to do that, do a comparison, I'll do data.comparisons ++, and that will, and we'll get that, right? Makes sense? Okay. Next, what am I getting? Okay. And then whenever I do a exchange, actually, so while this happens, the number of comparisons, right? So it's a while loop. So it's going to have one comparison, and then each time I am about to rerun it, I'm going to need to do it as well, right? Because I'll check before I enter the loop, and I'll check every time I get to the end of the loop right over here. That's a comparison right over here. Wow, this really isn't, we aren't counting as a comparison because this is this J here is an index. A comparison is only when we are comparing values and asking do they need to be swapped. And if they do, we do a data.exchange. And this is one of those kind of interesting ones where you're going to have essentially the unequal number. And what's cool is since I pass it in as an object, I don't need to actually return it, which is useful for when you're doing recursive functions and you need to pass down the data recursively. And this keeps you from having to like combine all your answers, which is great. And then we do one more exchange here regardless. Boom. Okay. And that's how I would modify insertion sort. Okay. And then we cared about what? We cared about the amount of time that was taken, right? So yeah, click here. Let's check how you can measure the amount of time that it took using nanoseconds. Don't really need nanoseconds, but we can modify this as well. We'll just need a long here. Long time taken. Time taken. Okay, and what we need to do over here is that basically we will do a long start is equal to, so to test how long physically something is going to take. It's very easy. You create a start time. You keep track of when it started. How you do that in any language, it all uses the system variable. So I'm going to use, rather than system nanotime, which is time in nanoseconds, I'm going to use system time in current milliseconds, which gets you the time in milliseconds, that the number of milliseconds it has been since January 1st, 1970 UTC. UTC being universal coordinated time. Every other date time thingy is translated from UTC. UTC is what we care about. It is yeah, the operating system may measure time in the units of tens of milliseconds. That is epoch time, and when they were talking about Y2K, they were talking about this value, an int of this value not being big enough to hold this value essentially. I I mean, that's a bit of an oversimplification, I think, but because there's other things involved there, other mistakes. But anyway, long current time in milliseconds, and then nanoseconds as well. So yeah, nanoseconds as well, which is as high resolution as it can go. You don't want to try ever to implement like something about keeping track of time yourself, because then you'll have to keep track of weird things like time zones, which are terrible and arbitrary. And oh yeah, leap seconds, they're a thing. Yeah, that's like when you get earthquakes and we need to adjust like the rotation of the earth like by that. What is a second anyway? You'd think, and it's actually measured by radioactive decay of a cesium atom, I think. So yeah. Anyway, long story, time is complicated. Let the computer handle it from you. So this is the current time in milliseconds since it's been since 1970. And then what we're going to do is that we are going to have a long start end. Bam. And now data.time taken is equal to end minus start. That's it. That's how we know how long it took. We simply take the number of milliseconds it took for the start and the number, we take them and then the number of milliseconds at the end, and then we subtract them. Okay. Now that I've done this, right? So you're going to do this for all your for all the algorithms here. Well, insertion sort, which I just kind of did for you, quick sort, and then one of your choice. So how do you do this now? Well, we want to test this algorithm on differently sized lists or arrays of integers. So a good test will have many data points of varying magnitude. And you should probably do averages. So what we're going to do is that you'll probably want to make a random array. So I'm going to go ahead and write a function for that. Public static. And normally I wouldn't give you this much, but it's summer and we have less time during the summer. So, you know, lucky you. Public static int array, make array, and it will give us one of size. And because we're going to be doing this a lot, we need a lot of random arrays. Public static int, make array, int size. This will make an array of, okay, right? It's an array, so technically I should call it length here, blah, blah, blah. Okay, move it over here. So we're going to make an array, and it's pretty straightforward. We are going to create an array of completely random numbers. So let's see. First thing we need to do is make the array. So int r is equal to new integer array of size n, size length, size length, return r. I like that. I like writing my arrays as r, my array variable as r, since we used to sound like a pirate for a little bit. R would be hard. So next, so now we've got this. Now it's just filled up with a 0, which is trivially easy to sort. Doesn't really give us a good representation of how these work. So we need to fill it with some data. So what we're going to do is random is equal to new. What we're going to need is I'm going to create a, we could make a new random number. Yeah, that's fine. New, we can do it over here. Just make a new random number generator each time. And again, random numbers in computers aren't actually pseudo-random. They're not actually purely random, because that gets into a whole philosophical debate about, is the universe completely deterministic, right? If I told you the exact variables of how I would throw something, would you be able to calculate it? The idea is yes. So is that die roll purely random? Gets into a weird philosophical debate that we're just going to completely sidestep and say it's statistically random. Okay, so we've got a random number generator that produces statistically random things. So let's see. Ooh, what is this? Ints. That sounds useful. Gives us a stream. Cool. I'll have to look into that. So random dot next int will give us a random integer, a completely random integer, right? So it can be anywhere between negative 2 billion and a bit to positive 2 billion and a bit. Let's see. We can also do next int in bound. I like bound because that gives us some other things. So giving it will give me a number between 0 included and the specified value exclusive. So let's just go ahead and say I'm going to take any number of values between 1 and 10, between 0 and 10,000 inclusive. So, and we're just going to have to do that for every single value in the array. So for I, boom, boom, r dot length, r is equal to, so the ith value is going to be assigned a random number. We don't know what it's going to be. Great. So what am I going to do? Well, now in my main for data collection, what I can do is I can say, hey, how long is this going to take on a so I'm going to add a toString here. String toString because I'll need something that quick. I'll be like toString. Exchanges plus space plus time taken. So there we go. Okay, so we've got that. And now what we're going to need to do is basically I want to test this insertion sort on various arrays of various sizes. So what I'm going to do is so what I'm going to do is let's go ahead and make a array list of data. I'll enter data list, new array list, boom. Okay, and what we're going to do is that we are going to so let's go ahead and say I want powers of 2. So for int 4, I'll explain. You'll see. I'll explain what I'm writing in a second. For let's go with we want to start at 6. So 2, 4, 8, 16, 32, 64. Yep. And then let's go with 20. Okay. Int n is equal to math.how 2 to the ith power. Now we're going to cast it to an integer so that it becomes an integer. Int r is equal to, okay, int array is equal to make array size n. And now if I want to test out the sorting, what I can do is I can do insertion sort. And now I'll do array data d is equal to new data. And I'll just simply do that. and then data list dot add the, but I'll go ahead and print it out the data here. So now I go ahead and I will run this monstrosity and hope it doesn't crash and burn on me, which is always a possibility. So here we go. Let's go ahead and stop this. So print out n plus, so we can make sense of this. So what I'm doing here is that I've written a for loop, and what it's going to do is that it's going to go and create arrays of size 2 to the i, of 2 to the i power. So the first array is going to be 6 long. Is going to be 2 to the 6, which is 64 items long, and then it will be 128, and so on and so forth. So if I go and I run this again, we'll see that I've got 64, 128, 256, 512, 1024, and notice that it's taking basically longer and longer each time. Oh, and it looks like it did so many comparisons here when we got to this point that I needed that these cannot be integers. They will need to be longs because they are going to be big numbers. Because otherwise they overflow, which is not a problem you have in like other programming languages like Python, but our problems you have in like C. So here I'm just here I'm running this, and this is the time in milliseconds it takes for that to be solved. So by doubling it, it should take about 4 times as long, but it could also take longer. Well, we'll see. So, and as you can see, this is a bit too much for even my my nice chunky laptop. That one took 20 seconds to do. Because again, this is in seconds over here. That is the number of comparison exchanges. So we'd be waiting a minute for the next one. So obviously that power is a bit much, but now that's something we have that we can graph. We could put it on a graph or something. So I would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 12. So I mean, we were getting pretty close. So I could do like 6 to 16, 6 to 6 to 16. Hey, that sounds pretty good actually. There. So testing on an array of this size, it took this many comparisons and exchanges. Now, if you want to get really good data, then, and notice what I've done is I've added it to the data list for later. Because what we can do now is that we can also, you know, if we want to print them out, but also maybe I want to do like an average of these things, right? So what I might do is that I might put another for loop here to run multiple trials on that same on power size n, and then create one data item that is the average of all those. Okay, so once you've got this, plug it into an Excel file and graph it, and basically show me that and what I'm expecting to see is basically an exponential, a polynomial time growth for insertion sort, and then log linear for the others.